Okay, 15 minutes left. Want to get started on example 1 for AC power. So let's bring that up. Okay, AC power. There are two examples. Example 1 is a 2-in-1 problem. The reason I call it a 2-in-1 problem is because we also perform analysis on this to determine the voltages and currents. So it's kind of like a chapter 5 problem. Okay. So we have a circuit, 3 components, RLC, including the source, excluding the source. And the question being asked is determine the power for every component. Okay. In this case, every component includes the source. Okay. So we're trying to find power for 4 different quantities, 4 different components. RLC, and then also the source. Okay. So what I'm going to do is I'll give you a couple of minutes while you're writing some of the initial problems down, and then I will go over the explanation for the first part of the analysis. Okay. Okay, so let's begin from the top. What do we have? We have 4 components. One is a source that is supplying the energy to these um, three passive components, right? Resistor, inductor, and capacitor. Okay. Think back to chapters 1 and 2. What do we need? If we have a resistor, Ohm's law and the power equation. V equals IR, power equation. P equals VI, product of the voltage and current. So if you're trying to find the power for either the resistor, the inductor, or the capacitor, we need either voltage or current and or the impedance for that component. So approach remains the same. Okay, the approach remains the same. So the approach is from chapters 1 and 2, right? Resistive circuit analysis. So as a first step, if you want to find the voltage and current, the first step in AC analysis is to draw out or redraw the circuit with its equivalent impedances, meaning the equivalent impedance diagram, which is what we do here. We draw out the equivalent impedance diagram where each component is replaced with its equivalent impedance. Inductor is represented by ZL, capacitor is represented by ZC, resistor, of course, is unaffected, remains the same, behaves the same for AC and DC. So resistor is resistor R. And you now have a circuit that is similar to a resistive circuit that we saw in chapter 2. So far, so good. Any questions? Okay. So then my suggestion, of course, if you think back to chapter 5, is to always draw out the equivalent impedance diagram, visualize it as a resistive circuit, and then form your approach. In this case, we see there's only one source. If there was more than one source, we would do either node voltage analysis or mesh current analysis or superposition. But we only have one source. And when we look at the combination of the impedances, we can see that it is possible to reduce the entire circuit down to one single equivalent impedance. So my approach would be to use the first technique, series parallel equivalent analysis, right? We can take R and ZC, they are both in parallel. We can reduce them to one single impedance. And then R and ZC in parallel, one single impedance would then be in series with ZL. And that summed up together would give you ZEQ, which you can then use to find your total current being supplied by the source. Make sense? Questions? Okay. So then we label all the currents. What do we have? We have the source supplying total current I. That current I makes its way through the inductor. So the inductor current IL is equal to I. It's flowing in this direction, of course, coming from the source. Enters the junction and splits in two. One goes through the resistor, the other goes to the capacitor. So I splits in two, and we can label it as, by applying KCL, I is equal to IR plus IC. Right, IR plus IC. Again, if the goal is to find power, and we have the resistance or the impedance, we only need to find either the current or the voltage, because we can use the expression P is equal to V square over R, or P is equal to I square times R. Okay. So I'm not working with numerical values yet. We are not putting in the numbers. We are simply deriving the equation. First, we'll form our approach, then derive the equations. Then we will look into the numbers. So right now, we have two impedances in parallel. Combine it together to get ZRC. ZRC is a parallel combination of R and ZC. We can see that ZRC is in parallel with ZL, which gives us ZEQ. ZEQ. One single equivalent impedance as seen by the source Vs. Okay, one single equivalent impedance ZEQ as seen by Zs. Make sense? I'll wait until students finish writing. And then once you have V and Z, apply Ohm's law to determine the current. V equals IZ. V is given to us. ZEQ is something we calculated. We can now find I, the total current I being supplied by the source. All right, questions? Any questions? So far, so good. Approach makes sense. Okay, so then time for some numbers. We look at our voltage source. The numbers come from the source, right? The source. In this case, the source is a voltage source, 10 sine 1000 t. Because it is in sine, we have to convert it to cosine. And we use the expression sine x is cos of x minus 90. Right? X minus 90. 10 sine becomes 10 cos 1000 t minus 90 degrees. Then you take that expression, compare it to the standard expression, obtain values for Vm, omega, and theta. Peak values, frequency, and the phase shift. Once you have omega, you can now calculate ZL and ZC. Okay. And as has been my habit and practice, I determine complex numbers both in polar coordinates as well as rectangular coordinates. ZL and ZC are standard expressions, j omega L and 1 over j omega C. Impedance, j omega L, that's rectangular coordinates. Polar coordinates is omega L with an angle of plus 90. ZC, capacitor impedance, is 1 over omega C, an angle of minus 90. Again, as a reminder, it comes from the fact that the voltage in an inductor always leads the current by 90 degrees and always lags the current by 90 degrees in a capacitor. Hence, impedance for an inductor is always plus 90, and impedance for a capacitor is always minus 90. Standard expressions. Okay, ZL is plus 90, capacitor minus 90. Once you have these values, you can go ahead and calculate ZRC. ZRC is two impedances in parallel. Similar to resistors, if you have two impedances in parallel, equation is 1 over R plus 1 over ZC, and the reciprocal of that resulting sum. It's only two in parallel, product of the two divided by the sum of the two. Hence, R times ZC divided by R plus ZC. Right here. Resistor R is given as 100 ohms. We can also write it as, obviously it does not have any imaginary component. So the angle for R is always 0 degrees. Or you could write it as 100 plus J0. Right? You've used both here. No imaginary component, no angle. And again, you need to be an expert in solving these equations on your own calculators. Okay, so we find ZRC as 50 minus J50 ohms. Let's take a pause. Let me know if you have any questions. Any questions at all? Nope. Okay, once you have ZRC, find ZEQ. Add ZRC and ZL, you get ZEQ. Once you have ZEQ, apply Ohm's law to determine the current I. Total current I. And that's it for the first part. Okay. All right, questions on the approach and all the steps that you have done so far? Does the approach make sense? Steps make sense? Calculations? Okay, so we'll end class here today. We'll pick up here again on Wednesday, that is tomorrow. Review examples 1 and 2. Take you 10 or 15 minutes so that you're better prepared to ask questions tomorrow. Okay, and I'll be in my office later this afternoon. If students want to stop by with any questions, I'll be happy to meet and answer them. All right.